Howdy, howdy. This is Mr. Potter. We're going to continue our discussion of using definite integrals to determine volumes. In our last lesson, we were talking about using volumes which we were dealing with cross sections. So given our function y equals radical x on some limited domain from 0 to 5, I was looking at the volume, and we determined that the formula for the volume was going to be the definite integral of my area function as a function of x. So I'm going to be dealing with this from x equals my lower bound, which in this case is 0, to my upper bound, which is 5. This is what we were talking about last time, using cross sections to determine the volume. What we're going to be doing today that's different is we're going to be taking a look at this as we're rotating about some line. In particular, in today's lesson, we're going to be rotating about the x-axis. So if I take a look at this graph, the graph of y equals radical x, and I look at this graph, but then I wanted to rotate it around the x-axis. That means that I'm going to have some reflection of my graph down here, and I'm going to see my cross sections actually being circles. Circles that are perpendicular to my axis of rotation, and whose radius is actually determined by the point on the graph. In this case, my r is really y. So for us, that's radical x. And I know the area of any circle is going to be pi times the radius squared. So I'm really dealing with pi times y squared. But if I want my area as a function of x, I actually want to replace y with radical x. So this ends up being pi times the square root of x squared, or pi times x. And so finding my volume of rotation, I'm going to be integrating from 0 to 5 pi times x dx. And pi is a constant we can take completely outside of the integral. So I'm doing the integral from 0 to 5 of x dx, the antiderivative of which is x squared over 2 times pi. And I'm going to be evaluating that from x equals 0 to x equals 5. So again, substituting, I'm going to end up with 25 halves pi. And so this ends up being my volume of rotation. Notice that the process is exactly the same as what we were doing yesterday. We're still finding our volume as a definite integral of our area function. But our area function has to be written in terms of x. What's different is because I'm rotating my graph around the x-axis. My graph actually extends below the x-axis and above. In the examples we were dealing with in our last lesson, all of our areas, all of our cross sections lay above the x-axis. And so when I'm calculating my formula of my circle, and of course the circle is always going to be area equals pi r squared. My radius is the distance from the axis of rotation to the point on my graph. So for our purposes here, it's really pi times y squared. And so we're going to get our area function, but once we get our area function, once we got this pi times x, everything else from this point forward was exactly the same as what we talked about last time. So I wanted to do a couple more examples of this, some with a little bit more interesting functions. So let's say that I'm dealing with y equals the exponential function, e to the x. And I'm going to be dealing with this on the closed interval from 0 to 2. So looking at this, I know my graph of y equals e to the x looks like my typical exponential function. It's going to pass through at 0, 1, and continue going out to whatever x is 2. But because I'm rotating about the x-axis, and all of these that we're going to be talking about in today's lessons are going to be rotated about the x-axis. So I'm going to have a mirror image function down here, and all of my cross sections are going to be circles. Whenever I do volumes of rotation, my cross sections always end up being circles. So looking at this, since my formula for area is pi times r squared, my radius is always going to be the segment from my axis of rotation to the point on the graph. So it ends up being pi times y squared. But we know what y is equal to. Y is equal to e to the x. And so my area function as a function of x is going to be pi times e to the x squared, or pi times e to the 2x power. So this is my area function. So this is what I'm going to be finding the definite integral of. My volume is equal to the definite integral from 0 to 2 of my area function dx. So this is going to be the integral from 0 to 2 of pi times e to the 2x dx. And pi is a constant that I can pull completely outside my integrand. I've got the integral from 0 to 2 of e to the 2x dx. And I can solve this by use of substitution. I can let u be 2x, so du in this case would be 2 dx, and I don't have 2 dx. All I have is dx. So I'm going to need a 1/2 du. So this problem is going to be pi times the integral from 0 to 2 of, in terms of u, this is e to the u times 1/2 du. Keep in mind, though, that this is really x equals 2 and x equals 0. So when I find the antiderivative, where I get the 1/2 times e to the u times the pi, and I'm going to be evaluating this from x equals 0 to x equals 2. This isn't a function of x. I need to substitute back in for x. And so I get pi times 1/2 e to the 2x, and I'm evaluating from x equals 0 to x equals 2. And so I end up with pi over 2 times e to the 4th minus e to the 0. And of course, this is a beautiful answer. It's a correct answer. It's not a decimal answer, but it's a closed form answer that we can use. So the key here is I need to find my area function. My area function, but not just any area function. It has to be an area in terms of x. And my volume is always going to be the definite interval of that area function from my bounds of integration. So, before we go on to our last example here, I do want to talk briefly about some identities that we need to be familiar with to get ready for the AP exam. In general, the basic identities that we need are our trigonometric identities that we're mostly familiar with. The idea that sine squared theta plus cosine squared theta equals 1. 1 plus the tangent squared theta equals secant squared theta, and 1 plus cotangent squared theta equals cosecant squared theta. These are what we call our Pythagorean identities. And of course, all of these come from the idea that when I'm dealing with my unit circles triangle, my x-coordinate is cosine of theta, my y-coordinate is sine of theta, and because it's a unit circle, my hypotenuse is 1. And so all of these can be determined either by the Pythagorean theorem or taking this first identity and dividing each of the terms by sine squared or cosine squared. But there are two other identities that we haven't had much call for, but now we're going to start using, and that's what we call our half-angle identities. And the half-angle identities that we're going to be using extensively is the idea that sine squared theta is equal to 1 minus the cosine of 2 theta over 2. Or cosine squared theta equals 1 plus the cosine of 2 theta, all divided by 2. And the reason that we're now dealing with these identities is because in the process of getting our area function, our area function being pi times my distance from my axis of rotation to my graph squared. If my y value is a sine function or cosine function, I'm going to find myself integrating pi times some trig function squared. And some of these trig functions are going to be a little bit difficult to integrate in this form. But I find that if I transform them into these half-identity, these half-angle identity forms, it's going to be much easier to find the antiderivative just by using substitution. So I wanted to do one example of that. So what I've got here, this is my little trig example. I'm going to be dealing with y equals the sine of x on the closed interval from 0 to pi. And again, I'm rotating about the x-axis. Now, I know that my graph of sine goes up to 1 and then back to 0 on the domain from 0 to pi. But because I'm rotating about the x-axis, I'm going to have, by symmetry, another graph down here, and my cross sections will be circles. The radius of each of these circles will be determined by the distance from the axis of rotation to the point on the curve. So my radius for each of these circles is y. So if my area is pi times y squared, I'm going to have my area function as a function of x equal to pi times sine of x squared. And this is what I'm going to have to take the antiderivative of. So my volume is the integral of pi times sine of x squared dx, evaluated from 0 to pi. And I end up with this sine squared that I'm going to have to deal with. It's difficult to deal with that unless I'm actually using those half-angle identities. So if I want to integrate sine squared x dx, I want to replace sine squared x with what it's equal to, which is 1 minus the cosine of 2x, all divided by 2. So I'm finding the integral of pi times 1 minus cosine 2x, all divided by 2 dx. Now again, this 2 is really a constant that I can pull completely outside. So I've got pi over 2 times the definite integral from 0 to pi of 1 minus cosine 2x dx. And the antiderivative of 1 is x. The antiderivative of this will, if I let u be 2x, then du ends up being 2 dx. And I don't have 2 dx. All I have is dx. So this ends up being 1/2 du. So I end up with 1/2 sine of 2x. And all of this is being multiplied by pi over 2. And all of this is being evaluated from x equals 0 to x equals pi. So when I go through my substitution, I'm going to have pi over 2 times x pi minus 1/2 sine 2 pi minus what happens when I substitute at 0. So it's going to be 0 minus 1/2 sine of 2, 0. And so I end up with pi over 2 times, this is pi minus 0. And this is 0 minus 0. I really end up with a volume of pi squared over 2. Now, it may look a little peculiar to have a volume that involves pi squared. Keep in mind that one of these pi's came from the volume of the formula for the area of a circle. That area of a circle is pi times my radius squared. And the other pi came from my limit of integration. If this had been a 3, then this would have been a 3, and my sign values would have been slightly different. But that's where the other pi is coming from. So even though it looks peculiar to have a volume that involves pi squared, that's my answer for this problem. When we're dealing with those trig identities, those 5 trig identities really are the big ones that we need to know for the AP exam, especially the BC exam. And it's those half-angle identities that we really haven't used much until this chapter. The idea that we have these definite integrals of trig functions squared, and it's easy to do secant squared. It's easy to do cosecant squared, but it's not as easy to do the integral of sine squared or the integral of cosine squared. And that's where taking these identities and rewriting it so that I can do this using a simple use substitution is going to make these problems a lot easier. So once again, this is Mr. Potter. I thank you for watching. Have a good day.